Hey guys, welcome to the third video in the Simply AI series. Today, we will be looking at an introduction to machine learning. We will look at introducing differences in types of machine learning, fields under supervised learning, fields under unsupervised learning, what is reinforcement learning, and fields under reinforcement learning. The main purpose is to introduce the names, big ideas, and provide a glimpse of some details. It is okay if you don't understand some of these details, as we will cover the important details, along with some concrete examples and applications later on. As we saw in the last session, machine learning is where a system learns from data, identifies patterns, and makes decisions. We also looked at two main uses, classification and regression. As you see here from the red box, machine learning is quite prominent, and as we saw in the last session, the advent of cheaper, faster hardware, especially GPUs, and abundant access to data due to the internet and smartphone technologies has made machine learning even more important. There are three main approaches to machine learning: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the system is trained using a large number of samples. Each sample is also labeled with the correct output that you would expect the system to predict. During the learning phase, the system looks at input samples, predicts an output, and compares that output with the actual output you provided to the system. If there's a mismatch, the system attempts to adjust itself such that there's a lesser probability of committing the same error. During the learning phase, the system learns the important patterns that help it to predict the correct output. Once the training completes, the system accepts an input sample and uses the patterns it learned during training to produce an output for this input sample. For classification problems, the output is a label, such as cat, dog, etc., whereas for regression problems, the output is a value, like the stock price, the drug dosage, etc. In unsupervised learning, the system trains using input samples to learn patterns in the data. It is different from supervised learning because you don't provide input samples and the correct output for that sample. You only need the input sample for training. Absence of this output makes it unsupervised, as we are neither obtaining the correct output for our training samples nor supervising if the system produces the correct output. So if it's not training with the correct output, how does the system know to produce the correct output? Well, that is what the training and pattern detection during this training is about. For example, during training for the k-means clustering algorithm, the algorithm determines k-centroids around where the samples cluster. These centroids are the so-called patterns learned during training. During prediction, a new sample's distance from these k-centroids is analyzed to predict which cluster the new sample belongs to. Clustering algorithms find inherent groupings of data, such as grouping customers by their buying habits. Association algorithms discover association rules between items in the data. For example, students buying study supplies also buy table lamps. The last form of learning is reinforcement learning. This form has gained tremendous traction in recent years and is quite fascinating. Have you ever wondered how a newborn deer, fawn, or calf is able to stand in 10 minutes and walk in just 7 hours? Actions which work, i.e. with cumulative rewards, are reinforced, and that is the idea behind reinforcement learning. During training, an action in a specific state that maximizes cumulative expected reward is reinforced. During a prediction, a set of actions are chosen such that there's a maximum expectation of cumulative rewards. Some of the exciting fields under this machine learning include dynamic programming, Monte Carlo, temporal difference, and deep Q networks. Some fields under supervised learning includes neural networks, a network of neurons trained to translate input of one form into desired output. Neurons are stacked in an input layer, output layer, and one or more hidden layers. Deep learning, using large neural networks with many hidden layers. These two form a bulk of machine learning applications, and we'll be looking at them in a lot more detail in a later session. Decision trees. Decision trees are structured as a tree of decision nodes, where at each node you decide based on some feature and traverse down the tree on a path based on that decision. The tree is structured automatically during training to predict a value by automatically learning simple decision rules from training samples. Support vector machines classify an input feature space by automatically finding an optimal hyperplane that divides it into spaces for each category. During training, the optimal hyperplane is found and used for predictions. Naive Bayes classifies using Bayes' theorem. It finds the probability of a sample being of a specific class using other readily computable probabilities. We will examine both the mathematical foundations and a more intuitive interpretation of this in a future session. Ensembles. One model is not rich enough to tackle some problem domains. An ensemble combines more than one weak model using different techniques. An ensemble combines more than one weak model using different techniques. Some prominent fields under unsupervised learning includes k-means clustering. K-means clustering is an automatic clustering technique where we form k clusters with minimum variance around each cluster centroid. This effectively splits your input feature space into k parts around a cluster centroid. A centroid represents the center of the cluster. This is a great technique to build clusters. However, its biggest drawback is that you need to know k, the number of clusters in your data, as a wrong value of k may lead to counterintuitive results. It has many interesting applications, such as targeting customer base for marketing, crime analysis, fraud analysis, and delivery optimizations. Association rules analyze dependencies between data items based on the pattern of their occurrences in correlation with other items. It automatically identifies rules on how different items are related. It has many interesting applications such as commerce analysis, medical diagnosis, and protein sequencing. Self-organizing map is a great way to create a self-organizing map of nodes, also called neurons, based on locality of training samples into the input feature space. Areas of the feature space with many training samples will attract more densely packed nodes. The spatial distribution of nodes indicates how data is clustered, and the final result is grouping of nodes based on patterns in the input data. It is a great way of automatic clustering, data visualization, and reducing data dimensionality. Self-organizing maps are indeed very useful and commonly used in many real-world applications. If time permits, we may check a detailed application using a self-organizing map. Reinforcement learning is one of the very cool, new, interesting AI fields. Consider a mouse who gets rewarded by a single piece of cheese as it moves to the immediate vicinity each time. However, if it ventures further, it may hit a jackpot of cheese, as shown here. Venturing further is, however, not completely without risk. Near the jackpot, there may be a hungry cat waiting for a tasty meal. The mouse is greedy, and its goal is to eat the maximum amount of cheese before being eaten by the cat. Should the mouse be content exploiting his knowledge of a single piece of cheese, or should he explore for the jackpot? This is a classic problem you face in many games, as well as many real-world scenarios. While playing a game, you win by doing things that you know will fetch you small successes, and that is called exploitation. However, you can't always win by doing so. Sometimes you have to take more risk. Take a hit now. Sometimes you have to take more risk. Take a hit now for a huge reward later on, and that is called exploration. This is the explore versus exploit dilemma, and reinforcement learning helps address it quite elegantly. Reinforcement learning is based on this idea of rewards. Consider a small kid practicing for a bicycle race in an unknown terrain. He tries going over it and falls down. He thinks, okay, that did not work. I can't do that again, effectively penalizing this action in this state. Another time, he tries avoiding the pothole by going around it. That took more time, but worked, so he thinks, okay, that did work. I should do that again in this state, effectively rewarding this action. Occasionally, choosing actions that carry more risk but higher expected rewards, like taking unknown shortcuts, makes it more likely to have an optimal outcome. If he never takes any shortcuts, he would never know they exist, and therefore he would never win the race on game day. Some shortcuts may not work and severely affect his timing during a practice run. But if he finds a shortcut that significantly cuts down on his time, that could maximize his cumulative expected reward. Note that unlike supervised learning, which learns to take the right action, the training in reinforcement learning is used to evaluate the taken action, i.e., evaluate the expected cumulative reward that could result from the taken action. Some prominent fields under reinforcement learning include multi-armed bandit, which is a class of problems where the system has only a single state and the goal is to select an arm from multiple arms that maximizes reward, similar to a slot machine you may find in a casino. Did you get the joke here? They're called bandits because slot machines always steal your money. In finite Markov decisions, the Markov decision process comprises a fixed set of states, actions, and model dynamics of the environment in which the system operates, i.e., we effectively know about the state transactions and the related probabilities. Reinforcement learning helps you to choose an action in a state such that it maximizes the expected cumulative reward. Dynamic programming includes techniques which assume MDP model dynamics are completely known. In other words, you have complete knowledge of this, the probability that you go to a new state S' with reward R while taking an action A in state S. In real applications, this is rarely true, and therefore these techniques are rarely used verbatim. But they provide a very important foundation of other techniques which relaxes this constraint about model dynamics. Monte Carlo methods have rewards that are based on final outcome experiences instead of model dynamics. It is hard to know the expected cumulative reward for taking an action A in a state S. Monte Carlo methods solve this by simulating such action and determining the actual cumulative reward from state S to a terminal state. It can be used only in applications where you are able to easily simulate the effects of an action. Temporal difference methods determine this expected cumulative reward without the need to simulate such actions. It estimates the reward for an action in a state by considering the immediate reward for the action in this state and combines it with the expected reward of the other downstream states. Thus, temporal difference requires no model dynamics or waiting for final outcome experience like in Monte Carlo. The most basic temporal learning algorithm which does this is called Q-learning, named after a Q table that maintains the expected rewards as a Q value by combining the action and the state. There are many other flavors of this algorithm, but the basic premise remains the same. Get the reward for action in the current state and combine it with the estimated reward of the neighboring state. As you continue learning, the estimated values in all states approaches the true value. This is highly efficient, especially for limited discrete states. We will look at how to use this efficiently in a sample application. And finally, in Deep Q network, the rewards are estimated using neural networks, and this works great when there are a very large number of states. We may also look at an example of this later on. So this concludes our introduction to machine learning. We will go in much deeper detail during later sessions for many of these fields, and also when we consider some comprehensive applications that make very heavy use of machine learning. Thank you very much for listening to this video, and I hope you join us for the next video, where we introduce reasoning. See you then!